Here's the problem statement. A man exerts a 400 Newton force to pull a wagon. The force is inclined to the horizontal at an angle of 33 degrees. The man pulls the wagon a distance of 12 meters in 10 seconds, and then there are two parts of the problem. A, how much work does he do? And B, what is his average power consumption? And your textbook has a diagram, which I don't think very much of, so I want to draw my own diagram here. So this is a fairly straightforward problem. We want to apply the work equation to figure out how much work the wagon is, or how much work the force does on the wagon. Now, there are several forces that are acting here, but we're only interested in this pulling force. Certainly there's a normal force, there's a weight force, there may be a frictional force involved. I would suggest that because the wagon moves horizontally and the normal force and the weight are perpendicular to the direction of motion, that neither of those will do any work on the wagon. The work due to each of those forces that are vertical would be zero. So let's work on this particular problem. So here's the work formula. We know that the force is 400, the distance that the object moves is 12 meters, and the angle is 33 degrees. So I'm just going to substitute those numbers in. Now make an observation here. The angle between the force and the displacement is an acute angle. I'm going to end up with a positive number for work. Yes, my object is moving to the left. Sometimes we think of the left as the negative direction. But because the force and the displacement are in the same direction, generally, or at least the component of the force that's causing the motion is in the same direction as the displacement, then the number that I get for the work is going to be a positive number. So let me put these in the calculator and see what I get. And without paying too much attention to significant figures, I get just over 4,000 joules. The unit for work is newtons times meters, and we call that a joule. Part B asks us for power. Now, I neglected to talk about power in the other part of my lecture, so let me just pause here for just a moment to talk about that. Over to the side, I'll write some things down. Ooh, Mr. Haynes, I thought this was an algebra-based course, but that looks like a derivative to me. That's calculus. Yep. Well, believe it or not, you're going to do calculus in this course, but we're not going to call it calculus. We're just going to define things in terms of deltas. It turns out that the power is the time derivative of the work. The formula, though, that's going to be useful to you looks more like this. The power is equal to the work divided by the time interval. And we don't put a delta with that W, and I suppose one might say that when we get to the work energy theorem, there's going to be a delta that appears with the energy. So the power is the change in energy with respect to time. For our purposes, though, we're just going to take the work and divide it by the time, and that number is going to tell us how many watts of power, if we were working with joules and seconds, how many watts of power are required to make this job happen. So let's apply that to the problem at hand here. I'll write down the power formula, and we have numbers now. We calculated a number for the work, that's about 4026 joules. I'm going to use my TI-89 calculator and hang on to all the figures that it gave me in the previous calculation. The time interval is 10 seconds. Well, I can do that in my head. 4026 divided by 10 is going to be 402.6 joules per second, and a joule per second is a watt. There it is. Now again, I haven't paid attention to significant figures, but I'm more interested in the understanding how to solve the problem rather than stressing the significant figures at this point. That's the answer to part B. Now I want to try another problem. This problem is the next example in your textbook. A 40 kilogram block is lifted vertically with constant velocity. Now that's going to be an important point when we get to later lessons, constant velocity. Nevertheless, constant velocity at a distance of 16 meters in 5.0 seconds. And we're asked three questions. How much work is done by the lifting force? B, how much work is done by gravity? And C, what is the average power consumed? So let's sketch a diagram. All right, so I've got this block that's being lifted 16 meters. Now, the block is being lifted with constant velocity, which is a code word in physics, which means that whatever forces are acting on it, those forces are in equilibrium. Well, certainly I have the earth pulling the block downward as one force. We call that the weight. So something has got to lift the block up, and your text kind of gives you a hint at that when they call it the lifting force. I claim that those are the two forces that are acting on this object. So I'm going to just quickly sketch a free body diagram of the block. So here's a free body diagram showing the two forces acting. The weight force we know is 400 newtons because they tell us it's a 40 kilogram block. We're assuming it's near the Earth's surface, so I can find the weight as 400 newtons. And since this block is moving with constant velocity, that means the lifting force must just balance the weight. The block's already moving. Newton's first law, the law of inertia, says it's going to keep on moving in the upward direction as long as those forces are balanced. So I can say that the lifting force is also 400 newtons. Now part A says, let's figure out how much work is done by the lifting force. The lifting force is upward. The displacement is also upward. The box is lifted vertically. So those two forces are in the same, those two vectors are in the same direction. The angle between them is 0 degrees. So the cosine of 0 degrees is going to be 1, and I can just multiply the force times the displacement and figure out what my answer is. So the lifting force does 6,400 joules worth of work. Part B, how much work is done by gravity? Now by gravity what we mean is by the weight force. Now notice that the weight force is downward, the displacement is upward, there's an angle between them, that angle is 180 degrees. And the cosine of 180 is -1. So the number I get for the work that's done by gravity, the work that's done by the weight force, is going to be a negative number. So the weight force does a negative 6,400 joules worth of work. Finally, the average power consumed. All right, now I think that this question is not very clearly asked, but I think the intention of your author is to figure out how much power is consumed due to the lifting force. So we're going to base it on that assumption. So I employ the power formula and I put the numbers in. And I get the power is just under 1.3 kilowatts. One final note in this topic is that we have a bunch of W's that are rolling around. So you need to be careful about your W's. W can sometimes refer to weight, W can refer to work, or W can refer to watts, the unit of force. I'm sorry, the unit of power. So use the context of the problem to help you know which W is meant. That's it.